We're with the Georgia NASA RERC at the Museum of Aviation, and joining us today is the Georgia Space Grant Consortium team that's based at Georgia Tech, and I'll let Dr. Kelly tell a little bit more about herself, and Lori Skillings, who is program manager for the Space Grant. But they're a big supporter of ours, and we really appreciate their not only participating in providing this information, but also being a strong supporter in us having the capability and the funding to do this. So I will go ahead and turn it over to Lori and Kelly, and enjoy.
Well, to say that Kelly, I hope, is going to be a really exciting and fun activity that you could potentially use with your students in your classes. It's, I think, something that's really fun and something that we've been developing and working on. Actually, Kelly has been developing and working on. So I really hope that you enjoy this. And if you've got any questions, throughout the session, I'll be monitoring the chat. And I don't know if Kelly you're planning on doing questions and answers like throughout or at the end, but I'll be monitoring the chat. I'll have myself muted, but if you need anything, feel free to message me throughout the message or throughout the workshop. So Kelly, it's all yours.
Great. Good afternoon, everybody. My name is Kelly Grunling. I am primarily a lecturer at Georgia Tech. I teach a number of the undergraduate aerospace engineering classes as kind of my day job. And on the side, I work as the K-12 outreach lead for the Georgia Space Grant Consortium. And the project that I'm showing today is sort of a mishing of my two worlds. One of the things that I've been working on is trying to help get more aerospace content that can easily be put into classrooms in the States so we can do a better job of developing our aerospace pipeline and really reach out to schools that maybe have traditionally been underserved and not helped much, not reached as well, I guess, from Georgia Tech and other places. So the activity that I have to share with you today is actually a derivative of one I give to my freshmen. It's sort of a simplified version of one that I give to my freshmen. And we've been, over the course of the semester, trying to make a modified version that's applicable to, I would say, elementary age, maybe upper elementary age students. However, as this is a derivative of something I do for my college freshmen, there's a lot of ways that we can adapt it to hit every grade level in between. So I will say, if you have questions, please feel free to interrupt me. I teach college students. I'm used to being interrupted. I don't mind it at all. And I'd much rather get the questions answered so that I don't lose you through the rest of the presentation. So what I'm going to do is just go ahead and share my screen, and we will get started. All right. Okay, so what I'm sharing with you today is an activity where you're going to design, build, test, fly, modify, fly again, your own glider. And to prove that this is entirely accessible to elementary school students, this is the one that I built. I don't know if you can see my camera at all. This is the one that I built. And this is the one that my son built. His is just a little bit fancier and nicer. He's in 5th grade. So that just kind of gives you more proof, if you didn't already need it, that kids are more creative than adults. So this project is based on, as I said before, it's based on something we do in our freshman level Intro to Aerospace course. And the goal of it is really just to give students an introduction to the design process. So how do we go about design? How do we sort of do that critical thinking that's required to have an idea, produce it, see whether or not it matches our expectations, and then figure out the right way to refine it to continue working towards a goal. It also gives them sort of that initial intuitive understanding of things like forces and balance of forces, and some of the aerospace concepts without them having to know all of the math and all of the calculus and all of the linear algebra and everything else. So it's meant to sort of be a hands-on way to get some of that intuition. It also supports, looking more at the K-12 level, the concepts that are done in it can support a lot of the math and science that's being developed in that age range. So the adaptation that I'm going to show today was sort of developed with the 3rd to 5th grade audience in mind. But like I said, if anybody has students at a different grade level and you want to talk about what adaptations could be made to make it an appropriate challenge at that grade level, I'm happy to meet with you and work on how to do that. So what the students are going to do is they're going to go through this process of design, building, and testing a small glider like the one I showed you. It's done with very low cost materials. Everything you need is a piece of cardboard, some kind of small stick. This is a barbecue skewer. You could use a pencil, you could use a dowel rod, some kind of small stick, some tape, and a tiny bit of Play-Doh. And one of the things I really like about it is there's infinity designs that you could come up with that would potentially work, right? There's no one right answer, but there's answers that perform better and worse, so students can iterate through and really sort of get a feel, build some of that intuition on how they can make their gliders fly better. So it's a lot of fun. Now, I'm sure one of the things that as teachers, everyone wants to know, it's what I always want to know with a project, is how does this map to the things I teach? So this is my attempt at mapping it to the school subjects I remember taking in elementary school. But I'm sure we could make a much improved version of this. When we talk about math, there's a lot of measuring, a lot of dealing with ratios, a lot of finding area kinds of things that are required. So if you're working with your students on any of these topics, it might be something that can really tie into a curriculum in that area. As far as science, we talk about forces, we talk about center of gravity, Newton's laws. So anything that's in that area, again, it's easy to tie into these kinds of topics. When I do it with my students, I have them do a report of some kind. Some semesters I do written, some semesters I do oral. It just depends what I'm in the mood to grade. But I usually do some kind of report where that includes sort of a discussion of their design choices, where they have to talk through their own thought process. We're actually working on developing a little history of flight video to go alongside this project. I'll talk more about that later. But I think the most important thing that it teaches is it really teaches those critical thinking skills, problem solving. How do you figure out what happened, correctly diagnose a problem, and then fix it, right? Those skills that are sometimes hard to learn when you're just working problems that use a specific process or a specific thing. So what I want to do today, that's kind of my overview of it. What I want to do today is actually walk through the project with you. I believe when you signed up for the workshop, there was information that if you came with this small set of supplies, something like a cereal box, some sort of dowel rod, some tape, that you might be able to try it yourself. Even if you don't have those supplies, a good part of this we can still do together. So what I was hoping to do is kind of have you do the activity to see some of the cool things that can happen as a result of the design. And then, this will be a very shortened version. It won't be the full activity with all of the steps. And then, at the end, we can talk about how to put it in classrooms, and I can talk about how we might be able to help you put it in your classroom. So this is the design process that we're going to use for the project. And Lori, this would be a good time to share the overall project assignment worksheet. Lori's going to put in the chat a overall, just sort of an overall handout that's meant to be handed to students. It's kind of a way to get started. But basically, what we're going to do with this project is we're going to start by learning kind of a crash course in aerospace principles. Again, no calculus, no linear algebra, just some of the important relationships that are necessary to make an aircraft that actually flies. We'll talk about an explore step, which we're going to actually skip today, but I'll talk about just a little bit what you might do with your students in that step. And then we'll focus on this sort of design, test, and improve. So we're going to design it, we're going to build it and test it, and then look at how can we improve it and make it fly better. But we'll start by simulating the learn phase. Now, a couple of things about this. I'm going to give you a super fast crash course in aerospace engineering. We are actually working on developing a series of short YouTube-style videos for students on the topics that are covered here that would be a little more detailed, but sort of more geared towards elementary students. We're hoping to have those available sometime in the middle of the spring semester. But we could also send a guest speaker to help with this part. So don't feel like you have to master the concepts of aerospace engineering to do this in your classroom. We have resources to help with this piece of it. So with that being said, I'll do just a really quick crash course in aerospace engineering. I hope you're all ready. All right, so the first thing we have to have is we have to have common terms that we use to talk about the airplane. So we have, I think most people are familiar with the wings. The body of the airplane we typically refer to as the fuselage. And then the other thing that's going to be important to our glider is the horizontal tail, which looks like the mini wing behind the main wing. And then the vertical tail, which is that thing that sticks straight up and down on the aircraft. So this is the terminology we'll use to talk about the parts of our glider. Most aircraft also has engines, but what makes a glider special is that it doesn't have any engines. Its only propulsion comes from that initial push or that initial throw of the aircraft. The other terminology that we need to know and be ready to talk about are the forces of flight. These are the things that actually keep an aircraft in the air. And this is what we have to balance when we want to fly any aircraft at all. So lift and drag are what we call aerodynamic forces. They're produced as a result of the air moving around the aircraft in the air. So the lift is primarily produced by the wings. It's generally perpendicular to the direction of flight, so it points up. It's what keeps the airplane up. And drag is something that we can't produce lift without drag, but it actually opposes the motion of flight. So drag's usually pointing backwards and going in the opposite direction we want it to. So drag's generally not something we want, but it's something that we have to live with because we can't produce lift without producing drag. Now, opposing lift, we have weight. So the aircraft has to have some weight. If we want something to fly, if we want it to rise up in the air, lift has to be more than weight. If lift is less than weight, then it'll head back down towards the ground. So if we want to take off, we increase lift. If we want to land, we decrease lift relative to the weight. And then the final force is thrust. This is what the engines create. It's what creates this forward motion through the air. In our case, our only propulsive force will be the throwing of the glider. So when we pick up our glider and we throw it, that'll be our entire propulsion force. Okay, so we call that thrust.
Hey, Kelly, I'm going to interrupt you just one moment.
Sure.
I'm going to have to try to share the documents in another way. Nichelle is saying that it's telling her that she needs to request access, and I don't know what else to do to give them access other than sharing the document right in here. So I'm going to try it again, but I just wanted to let you know that they don't have the document yet.
Okay, that's fine. I can share the documents in a minute on the screen.
Okay. I'm going to keep trying though.
Okay. I'll share them all too when I get to that part of the project. Okay, so let me pause. Is everybody with me so far? Are there any questions up till now? Okay. I will take that as a no. So let's keep going. All right, so when we talk about an aircraft, the biggest part of the design is going to be the wing, especially when we talk about these small gliders. So we're going to start by looking at sort of what we need in a wing to be successful at flying. So there's two things that we really focus on when we're talking about the wings of the gliders. One is the wing area. And this is like if you look straight down from the top of the airplane, the surface area of the wing is what we call the wing area. The bigger the wing area, in general, the bigger the wing area, the more lift we have. So increasing wing area tends to increase lift. And I'm skipping over a ton of physics to explain that, but just take my word for it today. Increasing wing area generally increases lift. The other thing that we care about, though, is the shape of the wing, which is, we use a parameter called aspect ratio to talk about the shape of the wing. And really what it is it's a measure of how long and skinny the wing is. We calculate it by which is the length from wingtip to wingtip, squared divided by the wing area. That's how we calculate it. And a bigger aspect ratio means our wing is long and skinny, And a smaller aspect ratio means it's kind of short and stubby, short and fat. In general, again, I'm skipping over a whole lot of physics here, but in general, a plane with a high aspect ratio has less drag. So remember, we want lift and we don't want drag. So we want wing area, but we also want a long, skinny wing. And those two things are sort of in conflict. Intuitively, right, as you make your wing skinnier, it's going to have less area. But on the other hand, it's also going to have less drag. So this is the big design trade-off we're trying to make as we design our wing. That make sense? All right. Okay, so gliders, again, I'm sort of skipping a good bit here, but gliders tend to have a maximum range when you maximize the lift to drag ratio. So the ideal flight condition for a glider is when this lift to drag ratio is maximized. So we're trying to do this design trade-off between increasing lift by increasing our area and decreasing drag by making our wings longer and skinnier. So in the classroom setting, you can explore different wing designs, different wing areas and different aspect ratios, and compare how well these different aircraft might actually fly. That might be an experiment you can do in the classroom. When we talk about the performance, there's really sort of two things we talk about, and they're related. The range, which is how far the glider went, and then the angle, which is the slope at which it returns back to Earth. So how sort of that angle that it's heading back to Earth as it comes down. And as you can see in the picture, these two things are related quantities. So you can measure the height from which the student flew it, the distance it went, and you can calculate the angle. Or you can draw a similar triangle on a piece of paper and have them measure the angle with a protractor so they can figure it out. So you can show them how these two things are related. And in general, the smaller the angle, the longer the range. So one other thing to keep in mind is that generally, if you minimize weight, you don't need as much lift to keep the aircraft in the air. So we also want to minimize weight in design. So if you're doing a unit, for example, on weights and measurements, you might want to have the students weigh their gliders and observe the way that weight is influencing the performance in the aircraft. So that might be something that can sort of be an add-on to the project. All right, so that's how we get the thing to stay up. But there's sort of a second key piece to flight. One is getting it to go, one is getting it to go straight. So when we talk about flying straight, we're talking about what we call flight stability. And that means that it doesn't do something crazy in the air, like pitch up, and that's what we call stall, pitch up and fall down to the ground, or nosedive and crash straight into the ground, or roll back and forth and do a big turn that you weren't expecting. So when we talk about preventing these things, right, we're talking about stabilizing the aircraft. And again, skipping over all the physics, this is why aircraft have tails. The tail is an important part of helping to stabilize the aircraft. This vertical tail here, I hope you can see my video. I can't see my video, so I'm hoping that I've got the right things in the camera here.
Yes.
The vertical tail is what stops it from going side to side, right? It helps keep it straight. So it stops it from doing this. This is what we call yaw. The horizontal tail helps control the pitching up and down. So getting this at the right angle will keep it sort of balance out, right? The wings are providing a lift force, which is pulling it up. The horizontal tail is counteracting that and helping it balance out. So this helps with the pitching stability. And then it's actually the wings help with roll stability. So for these small gliders, really the only thing we have to control is how much of a V we make. And I don't know if you can see my airplane has a little bit of a V here.
Yes.
It actually has a lot of a V. That's called dihedral, and it helps keep it from rolling to side to side. Okay, now these are little gliders made of cardboard. It's actually pretty challenging to perfectly balance them, but with a little bit of experimenting, you can get it pretty close. The last thing that has to happen for an aircraft to be stable is the weight has to be balanced. So you can imagine if there was a big weight on one wing, the aircraft is going to fly, or it's going to roll to its side and it's going to crash into the ground. If you have too much weight on the tail, it's going to go tail down and fall into the sky. If there's too much weight on the nose, right, it would go nose down. So getting the weight well balanced is a huge part of stability. And again, this is sort of an optional thing. This is an experiment that I do with my freshmen where I buy them these little wooden gliders that are, really inexpensive and that you just assemble really quickly. And I have them take Play-Doh and put it at different places along the glider and observe how it changes the flight. And what they usually find is there's some optimal range where if you put the Play-Doh in a certain range along the fuselage, you get the best flight. So we're not going to do this today, but spoiler alert, there's an ideal place for your center of gravity. There's an ideal balancing point. And so you can use this sort of experimentally to take a pretty good guess. And as a general rule, that'll be about a quarter of the way back on the cord is usually a pretty good place to make a glider stable. Okay, so this is a really quick in-class exercise that I do with my freshmen, but I've also done it with my 5th grader, and he was just as excited by it, maybe even more excited by it than my freshman. So I think it works at all ages. All right, so summarizing all of that, right? Summarizing what I just said, a huge part of designing a glider, one part is sizing it, which we talked about with the wing, and then the other part is balancing it, which has to do with designing the tail and getting the center of gravity in the right place. And balance matters. So that's where the Play-Doh comes in. Once we build the glider, you'll notice that this glider has Play-Doh on the nose. That's to balance it. That's to get the front to back balance correct. There's sort of an iterative process of throwing it, observing what it does, and then making corrections either to the tail, to the dihedral on the wing, or to the weight balance, more often than not the weight balance, to try to get the best possible flight and have it have a nice, smooth, straight flight to the ground. Okay, and again, skipping through some parts of it. So we are currently working on a video series that will do a much better job than I just did of explaining all of those concepts at an appropriate level for elementary school students. So we're hoping to roll that out soon. But in the meantime, we can always send a guest speaker to come and talk to the students about aircraft flight. Okay, so that's the learn phase of our design process, is just give them that initial bit of information that they need to feel confident to get started. The next stage is explore. So once they kind of have some basic understanding of what's going on, we might ask students to go and look at examples of real gliders and make observations. Maybe we have them take measurements from pictures, compare what's similar about their wing shapes, what's similar about their tail configuration, what's different, what are their aspect ratios, what are their areas. We could ask a million questions, right? To let students try to just understand from looking at existing gliders. And then once they have this, like we might say, how big is the horizontal tail relative to the wing? And they might discover that for most gliders, it's about a quarter of the wing area. The horizontal tail area is about a quarter of the wing area. So they can kind of uncover some of these relationships that will then inspire them as they go into making their own design. We're going to skip this stage today. And we're going to get into how the actual design process works. So before I go any further, I want to stop and give a chance to ask questions again. Go back to my... Are there any questions so far? Have I completely overwhelmed everyone? I hope not.
No, I was listening. Actually, you are going to send this to us, right? Because this goes beautifully with using Puzz Matrix like we do with my kids, and that's just perfect to go with it.
Yeah, we're going to send everything that we do over the course of this.
Okay, because that is awesome.
All right. So let's talk about the design phase. So let me switch what I'm sharing. Give me 1 second. Switch gears here.
Are you ready for me to share the other files now too?
Yeah, if we could share all, if we just go ahead and share all of them.
Yep.
I've got to figure out where my screen sharing button is. There it is. Okay. So let me switch gears here real quick. And all right, can everybody see again my window? Okay, so I have made a couple of worksheets. Again, I'm thinking of the 3rd to 4th grade, or so, like 3, 4, 5 grade range. We can adapt them. We can make versions for other grades. My only testing of this has been to make my 5th grader read through them and try to do it. Again, he produced this, which looks nothing like any of the templates that I gave him. So creativity wins. But so I'm definitely open to suggestions for improvements. But so my thought of how this would work in an elementary classroom would be we'd start with this worksheet here, which just introduces, has a couple sentences at the top explaining what a glider is, tells them this set of materials that they have, my little set of materials, and gives them a design goal, which is a glider that will fly straight for at least 10 feet. 10 feet's pretty achievable. Most of the students will be successful with that. When I give this to my college students, they get a significantly larger distance and are generally able to achieve it. They also have access to slightly better materials. So, but 10 feet is definitely something that, you know, with iterations, most of them should be able to achieve. And then I just show them the design process. So they do the learn and explore. And then when we get to the design, I have a series of worksheets that I've been working on developing to help them sort of structure their design a little bit and kind of give them, handhold them on their way through so they're not completely lost in space. And I've geared these towards trying to tie into some of the topics that I know are covered in upper elementary math. So things like ratios and area, trying to make sure that there is a tie-in to the actual curriculum here. If you were, for example, in high school, there's a lot of things we could do tying into, say, a trigonometry or an algebra curriculum that are, you know, that are not going to show up in these, you know, 3, 4, 5 geared worksheets. But these can be modified. Again, you know, the challenges can be modified to be appropriate for any grade range. So you're just seeing one iteration. Okay, so generally we would start with the wing design. And so in this case, I have given 3 examples of standard wing designs that you might see on a glider. And if they had done the explore phase, they would see that most gliders have something that looks kind of similar to one of these 3 designs. And it shows you the key measurements you need to make, and it gives you, you know, you can circle the one you want to use, talk about why you want to use it, and then at the top you can summarize it. So which shape you're using, how long do you expect your wing to be? I would say don't let them do more than like 8 to 12 inches if it's made out of cardboard or it becomes too flimsy and doesn't really hold up. And then you can have them calculate the area and the aspect ratio. So they can break this apart into different shapes, right? You can see, like, for example, the trapezoidal wing, you can break it apart into a rectangle and then 2 triangles that they then have to calculate the area and add it together, put those math skills to work. You know, similarly with the trapezoid or the tapered wing, you can divide it up into rectangles and triangles and have them calculate different, you know, the areas of their different wings, and then they can also calculate their aspect ratio through this span squared over area relationship. The other thing is they can start thinking about where they want it to be on the fuselage. This is something they hopefully would have discovered during their explore phase, is that the wings are typically about midway on most airplanes. Some of them are a little more towards the front or a little more toward the back, but they should have a pretty good idea of where they might want to put it on their fuselage. And then everything else we do from this point, I have related back to the size of the wing. So once they have their wing, they can use that information to help them figure out the right size for their tail and then the right size for their overall glider, their fuselage. So I don't know how many people actually have the supplies if you want to try it. Or if you'd rather I just talk about the project and go to discussion. I'm happy to kind of go either way. I know the online setting, if we were doing this in person, I would have had supplies for everyone. With the online setting, I'm happy to do whatever is more comfortable for the audience. Are there any opinions on that? We can take a vote. Does anybody want to try it, or would you rather I just talk through it?
I'm all for just talking through it.
Talk through it. Talk through it. All right, that seems like the overwhelming vote here. So I'll just talk through it, and we'll give you all the worksheets so you can try it on your own time. All right, so this is the wing design, and that's really, it's kind of counterintuitive, right? We're starting with the wing and working our way to the overall glider. But the wing is such an important part of the aircraft that it's a really good place to start, and we can sort of reference everything else back to this. So once they kind of get their wing design in place, they can start thinking about their tail. And I didn't give a lot of options for the tail. I sort of did just a standard rectangle horizontal tail with a triangular vertical tail in my worksheet, but I could update this to give them more choices of shapes. But this is kind of like, you can think of it as a math challenge problem for them. In general, horizontal tails have an area that's about a quarter the area of the wing, so 1/4 the area of the wing. So the challenge to them is to figure out a span and a chord, right? Again, span and the chord are labeled in the drawing, that'll give them an area that's 1/4 of what they calculated before. So there's a little kind of math challenge if you happen to be doing ratios or similar fractions or whatever in your math class. There's a little math challenge in there. And then similarly for the vertical tail, the area should be about, if you did the explore phase, you might discover that the vertical tail should be about 1/10, give or take, of the area of the wing. So you have to figure out a height and width that gives you an area that's about equal to that. And we can make this challenge easier or harder based on the grade level. So for example, you could fix their width, tell them how wide it has to be, and just have them calculate the height. If you had younger students, you might just give them 3 choices of shapes with dimensions and just let them pick one. And so again, this can very much be scaled to match different age ranges. And that's one of the things I really like about it, is the same thing that we're using to challenge our freshmen at Georgia Tech can be used to challenge elementary school students anywhere, or high school students, or wherever. And then the last one, so once you kind of know the size of your wing and your tail, the next step is really just to put it all together. And so I've kind of given instructions for how to make a couple of really common views, the top view and the side view, and then which dimensions that they might want to label on that drawing. Doesn't have to be done this way, but the idea is to help them sort of sketch out what is it it'll look like. What will it look like from the top if you look at it from this direction, and then what will it look like from the side, and let them figure out, where do I want the wing? Where do I want the tail? So once they have all this information, they can go ahead and actually build their glider, because they have everything they need. So they can cut out cardboard that makes that wing shape of that wing size, that tail shape and that tail size, and then they can tape it all together. And you can see I used much tape for mine. My son, I don't know if you can see it, he used very little tape for his, and he used Scotch tape because he didn't want it to be, quote, making his glider ugly. So if you think the kids won't care about the glider, we really got attached to our glider, and we had a hard time handing it over to mom when we were done to use in her workshop instead of putting it up in our bedroom. So anyway, so they can actually go and put their glider together. So we'll send you, with the materials from the workshop, we will send you all 4 of these worksheets that I just showed. And again, if you have an older age group or a younger age group, or you want to challenge your students in a different way, I'm happy to work with you to adapt any of these to make it more appropriate for your classroom. So give me 1 second. Let me switch back to my PowerPoint here.
And if anybody wants to download those now, all 4 of them are available in the chat. So they should be available. If you click on the 3 little dots to the right of the file name, you should be able to either open online or download. It might, if you open online, it might give you the option, or should give you the option, to download and save it.
All right.
Can you email that to us also, please? Because I'm on my phone and there's no way to load it from here.
Yeah, Claire Swinford at the Museum of Aviation and Miss Patty, they both have the presentation as well as all of the worksheets, and they will be emailing those out to every participant.
Awesome, thank you. And I will take you up on your offer of adapting it because I'm thinking my second graders with a little bit of graph paper could actually do some of that stronger math.
So I'll tell you, I did this once with a group of second, third, and fourth graders. It was a mixed age group. And we did a slightly different variation on it. So I actually got balsa wood. This was for my son's class, or my son's science club. It was actually science club. I got a bunch of balsa wood and went to the makerspace at Georgia Tech and cut out a bunch of wings, different shapes and sizes of wings and tails, and had them just sort of mix and match and make little gliders like this and test them out. And when they were done, I had them write down their observations. So as a group, they all sat down together and they made a bunch of observations. And the next week, we came back and gave them effectively this set of materials and had them design their own. And they were very much able to take the lessons from using kind of the pre-made ones and apply it to make their own. And they had some of the coolest airplane designs I've ever seen. And I swear to you, some of their airplanes flew better than what my freshmen produced some semesters. So I think it's very doable at second grade.
Yeah, my kids are gifted, so they're a little bit higher anyway. But yeah, I'm thinking it's very doable. And I'm thinking the math, especially the area, because they're already starting to try to play with multiplication and division a little bit. I think that's a great idea to be able to play with it some. They may not get it 100% right, but they're heading in that direction. So I'm thinking it would be good.
Yeah, I would love to work with you to make a sort of slightly younger kids version. So full disclosure.
Kelly, I was going to say, before you go on, I was going to say, Kurt in the chat has asked if you could show your examples. He's only seen the slides, so I'm wondering if you went back just to camera view, we could get a full on screen and get a better view of the actual, the two gliders that you have.
Actually, let me do this. I have photos of them, and I think that might work the best. Give me 1 second, pull up the right document. So I actually, the reason that we're targeting the 3rd to 5th range is we're working on a pilot project for this, to kind of develop all this material with Centennial Academy in downtown Atlanta. So I have a lot of this has come from working through it with them, and they're planning on rolling it out early next spring. But let me just really quickly, why will it not let me? Give me 1 second. I'm sorry. I'm figuring out my computer. Oh, I see. Okay, so here's, I don't know if you can see this any better. The one over here is one that I made. This
Zoom
is
in just a little bit.
My kid made. Okay, so the one on, I guess, the left is the one my kid made, my 5th grader. And the one on the right is one of the ones that I made. Mine all look a lot alike. The one in the middle, I don't remember who made. That was part of a different prototype. But there's some examples of what they look like. And so you can use fancier material. Like I said, I've done it with balsa wood too. But what I like about the cardboard, it's like basically cereal box material. So it's very accessible to anybody, regardless of classroom budgets or income level. You know, it's a cereal box and a barbecue skewer, basically, and some Play-Doh. And so it's something that most kids will have access to, and that can be put in a classroom for a relatively low cost, even with a large group of students. So does that help, Kurt?
Yes, that looks good.
Awesome. Okay, so let me go back to my slides. Gotta love this virtual world we live in. All right, share. Okay, so those worksheets are there to help with kind of this design phase. And then once we have that initial design, so once they get started, the next thing they'll do is they'll go through this process of balancing their glider, which is really just, you know, testing and improving and testing and improving and testing and improving until the glider flies the way that they want it to. So understanding that we need some just good rules of thumb for how to balance a glider, I sort of have made a little process here that has some common problems and then a few ideas of what typically works to correct those problems. So you start out by just putting some Play-Doh on the nose. I've never seen one of these that doesn't need at least a little bit of Play-Doh on the nose to fly. So we start by putting a little Play-Doh on the nose, and the goal of that is to sort of move the CG towards the front. In general, stability happens when the CG is towards the front of the wing. So you can actually kind of just put it on your finger and find the place where it doesn't fall forwards or backwards, to sort of figure out where along the fuselage the center of gravity is, and then have it just, basically doing this until it balances. So you want the CG to be about a quarter
a little
of the
bit
way.
more. You were a little lower
Sorry.
of the camera.
Sorry. So I'm just, basically balance it on your finger, figure out where it's more or less balanced. And you want the CG to be about a quarter of the way back from the leading edge is a good starting point. I don't know if you can see.
Yeah.
About a quarter of the way back. For most gliders, that's a pretty good starting point. And then you throw it a few times. I generally tell them, don't just throw it once, because a lot of times they'll do something weird on one of their throws. It'll do something crazy, but it has nothing to do with the glider. It's because they threw it straight up or something like that. But throw it a few times and see what it does. If it's pitching up, you need more Play-Doh on the nose. If it's pitching down, you need less Play-Doh on the nose. If it's rolling from one side or the other, most of the time they've got a little bit of a weight imbalance, or their wings are a little bit twisted one way or the other. And so I've kind of put just some basic troubleshooting things that generally work to correct particular flight performance issues. Sometimes it could be that they tape the vertical tail on a little bit crooked, things like that. And it's the same advice that we go through when we do this project with the college classroom. Really, it's the balancing the glider is really important to making it fly well. And I observe with my college students that I can tell you who spent a lot of time testing and who built a glider and showed up on the flight. So we have a fly off when we do it in college. We have a contest, and they come and have a contest for whose glider can go the furthest. We do it like a March Madness tournament. It's a lot of fun. But I can tell who actually spent time balancing their glider and who put it together 5 minutes before class and showed up and hoped it flew well, because this balancing really is a pretty important stage of it. And what's great about it is it gives that sense of like, okay, I designed it, I built it, I observed what went wrong, I corrected it, I understood like the cause and effect, I saw this action, I did this to correct it, right? I saw that it improved or that it didn't improve, so I tried something else, and they can kind of iterate through that. But it gives that sense that not being perfect the first time or failing the first time is an opportunity to improve and learn, rather than something they should be worried about, right? It's actually just helps you learn and be more successful. So once they do this a bunch of times, eventually they'll have one that they're happy with and that flies decently well. And so they can talk about not just what they did to build it, but then what they actually did to improve it. And so getting them to communicate about that, I think, is a big part of the learning process. So when I did this with the group of 2nd to 4th graders, at the end of it, we had them all stand up and talk about their glider and how they made it fly well. And so it was interesting because they could very clearly explain the cause and effect of things that are actually very complex aerospace principles, but they could explain it in very simple terms very clearly because they'd observed it on their own glider performance. And it did give them a chance to sort of use that cause and effect type language and really understand how they thought about it and how they did the design, which I thought was really cool to see with these younger kids. So I don't like to leave it as you built a glider, yay, it's very nice. I like to do some kind of all class closing activity. There's all kinds of things you can do. If you're a math teacher, you might make a plot of everybody's and look for trends. You might plot like aspect ratio versus distance and give everybody a sticker to put their aspect ratio versus distance on the plot and make it on the wall, that kind of thing. You can have students, if you're, again, older students, have them do a bunch of flights and calculate the mean and variance, or the mean and standard deviation of their flights. You could do comparisons between the gliders that flew the farthest and see what they have in common and what was different about them. you can have everybody give a short presentation or a report or a written report, or the list goes on. There's lots of ways that you can then bring the whole class back together so they're not just learning on their own, but they're also learning from each other and learning from the group performance as a whole. I know also that a lot of schools like to have a theme that carries across all the subjects. So obviously this project is quite high in science and math concepts. But I know the schools that we've worked with have said, well, we'd love to have a way to tie it also into things like art and social studies. And so I've also been brainstorming some ways that we can sort of some related activities that could be done in other subject areas that would kind of give a nice little aviation theme across all the subjects. So these are some of the ideas I came up with. Full disclosure, I am not an art teacher. I am not an artist. You saw my glider versus my kids. I have no art skills. But I've tried to think about how you could make kind of an aviation tie-in in some of the other classes. I'm sure someone who actually teaches these subjects would be far better placed to come up with some of these ideas than I am. But I will say this, if you want recommendations on good biographies of aviation pioneers matched to different grade levels, I probably have some recommendations for that. And if you're interested in something about exploring the impact of aviation on either society and globalization or on the environment, there are people at Georgia Tech that would probably be interested in talking to your students. And so we could probably arrange something in those areas. And then finally, again, if you wanted to have a discussion with your students about what kinds of jobs are there in aviation, I have friends who have a presentation on this topic, and they actually specifically will talk about in Georgia what kind of aviation jobs are there and where would you go to school and kind of what would your future look like. And so these are things that we can help with in some of the areas. You may be on your own for the art and poetry, though. It's really not my wheelhouse. So that is everything that I had to share with you today. I'm happy to answer any questions, or I'm open to any discussion on how to make it more appropriate to your classrooms, whatever you want to do with the time that we have left. So I'll just open the floor.
Will you be sharing the link of the recorded video?
Lori, that's for you.
I will be sending the link of the recorded video once it's ready back to the Museum of Aviation, since this is actually one of their workshop series, and then they will be sharing that in whatever format that they plan to share with. But yes, the recording will be available, the slides and all of the handout, the worksheets will be emailed to you, so you'll have everything.
Thanks.
And Yolanda, this is what I'm planning on doing with your group.
I know.
Next week. Okay.
Thank you. Sorry, I'm a little bit late.
They're going to do sort of a short version of this because I think we only have about an hour. But yeah, this is sort of a.
And that's fine. I will just want to kind of prepare for some troubleshooting. And I did get your email, everybody's emails. It's just been fun on this end.
I'm sure it has.
But I'm going to probably call you this evening or tomorrow anyway because I have your number. Thank you.
Let's do it tomorrow. I promised my daughter that after this, I would help her make an advent calendar.
Absolutely. Oh, that's so great. Yes. Perfect. Tomorrow's fine.
Yeah, back to those art skills I don't have. Luckily, she's got some.
Cool.
Well, if there's no questions specifically to what's been shared, I would like to ask the participants, is this something that you can see utilizing in your class? Is this something that you could see integrating into, what you are teaching to your students? We got some people typing. Awesome.
Teaching space. Awesome. That
sounds wonderful.
I think this is great. And also, Kelly, towards the end, when you were talking about, it's built, a lot of critical thinking is built in and problem solving. And that's what's good. and what our students need, and even some of our adults, we need that. But it's a fun way. They're already excited. Of course, they want to solve the problem and try to get their glider to fly faster, but they are coming up with the answers. And even if you do it collaboratively, they can hear what one person is doing. But the good thing is also you also have something to guide them, to show them, so they're just not out there in the ocean by themselves. But you do have some kind of guidance, but it will help them with the critical thinking, and it's built in for success.
That's the hope. That's definitely the hope. Josh, I'm seeing your question in the Zoom about doing Zoom lessons. So we are going to try, I believe with Yolanda's class, we're going to try doing this over Zoom. That'll be the first time that I've tried. I've done it a few times at my kids' school, not over Zoom. But the plan is, yes, to be able to do a Zoom version of this. Definitely will need support from the teacher in successfully doing it over Zoom, I think. But yes, and given that you're studying space, I will also throw out there that we have a group of students that we call our Got Space team that is willing to come and do presentations, again, over Zoom, to classes on various topics related to space and astronomy. And so if that's something that might be interesting to you also, sort of separately from this glider project, you can send me an email. I think my contact information is getting sent out. I think Claire is going to send out my email. You can send me an email, or Lori can put something in there.
Yeah, I'll link to the
if that's something interesting, you might be able to do that.
I'll put a link to the Got Space page right here in the chat. So that website has more information about the Got Space program, some of the current presentations that we have available. But if there's something that that maybe is in addition something you're seeking, you could also send us an email. And we have an email address, gotspace@gatech.edu. It will go straight to me. I don't know that it goes to Kelly, but it will come straight to me.
No, it doesn't come to me. It goes to you.
But I can forward that. I can forward that to you. But Got Space, it just stands for Georgia Outreach Team for Space. So that's the intent of the program, is to really kind of outreach to any students or any focus of outreach to has a motivation of space. So it doesn't actually have to be rockets or planets or getting to space, but it could potentially be growing in space or all sorts of things. So it's really every topic is potentially, I think, available. So it's just a matter of whether or not we can find the expertise to match the questions and the needs.
And I popped my email in the chat. And again, I know I kind of focused a little bit on the grade levels that we've been working with, but I'm happy to work with anyone to adapt this to different grade levels. I think my hope would be eventually to have kind of a portfolio where I can pull the right book off the shelf to match, whatever grade level or subject we're dealing with. So I think if nobody has any questions, we can let you all get on with your evening. Thank you so much for coming and listening.
Yes, thank you guys very, very much. And I'll even pop my video back on so I can wave and say goodbye. But we thank you for your time this afternoon, this evening, and we hope this has been helpful. And if we can be of assistance to you in implementing and rolling this out with your school, with your class, please don't hesitate to let us know. Great, Josh. We look forward to hearing from you.
Thank you so much. That was a great workshop.
Thank you, Patty.
Happy to do it.
Claire.
All right, I'm going to go ahead and stop the recording.